Hi everyone, welcome to today's class. So this is my topic number 13, and for topic number 13 I have chosen one inorganic chemistry topic. And in inorganic chemistry for CSIR-NET or GATE, this kind of exams, actually two major chapters are there, which are one is coordination chemistry and another one is organometallic chemistry. And sometimes many tricky questions are actually asked from these topics, and student can't actually attempt that questions. So, but this topic which I have chosen today is comparatively easier than the other topics in organometallic chemistry. And if you know how to calculate the 18 electron and if you know the basics of it, you can actually answer many questions. Okay. So from this topic, actually, in every CSIR-NET, 2 to 3 questions must be there. So if you know, if you have a clear idea about this, so you can attempt those questions. So let's start, and please make sure that you have a pen and paper with you so that you can practice with me, because many PYQs I have incorporated here. And one thing is that uh, please be attentive. Okay, so that you can't miss the important some points. Okay, so let's start. So now first question is organometallic compound. What is a organometallic compound? Fine. So you are thinking, yes. So organometallic compound, if we just differentiate between these terms, we know that it is organo and metallic. Okay. Organo means which we know. Organic compounds. Organic compounds are made of carbons, right? So carbon based compounds, and metallic means metal. So the definition, if you see that the compound which has at least one bond between carbon of a organic species and metal. So MC bond is very important here. MC bond must be present. Okay. So for that only we can say that compound is organometallic compound. For example, we know that Grignard reagent, so that is nothing but a organometallic compound. Here you see RMgX means R and Mg, here R minus and Mg plus, this kind of polarity difference is there, and this butyl lithium also the same thing. Gilman's reagent we know R2CuLi, etc. These are some example of known organometallic compounds, and also the, let's say, when we take any metal and carbon bond like CH3. Okay, so this way also we can represent the organometallic compounds. No, but there are exceptions. What are the exceptions? So NaCN is not a organometallic compound. NaCN is not a organometallic compound. So why we are thinking that it is it can be organometallic compound? Because it has CN, and CN is nothing here. It is NaCN, right? So through C actually it is bonded, but here it is a ionic kind of compound because it is a sodium salt, right? So it is exists like Na plus and Cl minus. So no true sigma bond present here. Okay, ionic bond is only present here. And another important thing of organometallic chemistry or organometallic compounds are that M, let's say in any organometallic compound, M, the oxidation state of M can be changed to, let's say, M plus 4 plus 6, etc. So it is a actually property of organometallic compound that their metal can actually vary or can exist in various oxidation states. But here it is not the case. Okay. So in that point of view also we can say it is not a organometallic compound. Now first organometallic, this is for only your general knowledge. So first organometallic compound of transition metal was the JSS salt. Okay, this is the structure, or this is the formula, okay, of JSS salt. And the first OMC organometallic compound of main group element is cacodyl oxide. Okay, this is arsenic, oxygen, and arsenic CH3 bond is there. So this is the first OMC of main group. Fine. Now we have to know about the hapticity. What is it? Okay. The total number of donor atoms of ligand attached to a metal. The total number of, not electrons, nothing. The total number of donor atoms of a ligand attached to metal. That will be the hapticity. It is denoted by eta to the power x, where x is the hapticity. Okay, number of donor atoms attached. Fine. For example, let's say this one. Okay, one organometallic compound has M and this allylic bond is there, and it is only attached to the it is only attached to the this carbon, this corner carbon. Okay, and here same allylic ligand is there, but here if you see it is attached to the corner carbon and also the sigma bond, sorry, pi bond. Okay, this kind of dashed bond I have shown to show the interaction between these two. Fine. So what will be the hapticity of this both case? Because metal is same here, ligand is also same. So metal and ligands are same here. Only difference is the attachment sites. Okay. So it is attached with one carbon. It is attached with one and pi bond between two carbon, right? 1, 2, 3. So it is attached with 3 carbon. So it will be eta 3 and it will be eta 1 compound. Fine. So if in any question it is written, okay, it will be eta. Okay, let's say it is written. Now how can we draw the complex? So it will be PT. Okay, C3H5 means 1, 2, 3, 1, 2, 3, 4, 5. Okay, so it is allylic only. This one. Okay, so eta 1 means again same. This, and eta 3 means we don't represent like that way. We know that it will be through 3 carbon. Okay, so let's show the pi bond cloud like that way, and it will be attached with this. So these actually in the question you can be asked, or it is written that eta 3, eta 5 or something like that way. So you have to understand that their bonding is like this. Okay. If let's say, okay, if let's say eta 5 will be 5 carbons are involved, right? This one will be eta 5. Okay. It can show eta 1 also. How? Let's say double bonds are here and it is forming bond only through this. It will be 1 carbon only, it is joined, so it is eta 1, but it is eta 5. You understood? So you see just how many carbons are attached with metal. That will be your hapticity. Fine. Now here is triple bond and CH. So you must be thinking that 3 bonds are there, it should be eta 3 then, but it is not. It is not eta 3. It is, so in the definition itself, you see total number of donor atoms of ligands attached to the metal. So here ligand is, let's say, CH3 minus and the atom, carbon atom only attached with metal. So it will be eta 1. See, if you remember the definition in a correct way, you can actually never be disappointed or never be wrong in the question. Now, electron contribution. Okay, we know that how metals are attached and how we can represent that, but we have to actually count the electrons, because in the 18 electron rule, we have to count the total electron of a metal. So, electron contribution. So, two methods are there, neutral method and ionic method. So, I will be teaching you, or it is my advice to you, that you should practice in neutral method only all the questions, so that you can never be confused. If you know both methods like neutral and ionic both, then you can be confused in the exam hall, that how many contributions of the one specific ligand. Okay, so it is preferable, or I will advise you only to focus on one method and properly learn it. In a proper way, please learn one method, then you can answer any question. So here one thing is that neutral method, so bonds will be homolytically cleaved. Fine. So metals are actually attached with ligand or carbon, let's say, but via sigma bonds. We know coordinate bonds are there, but as a result it is sigma bonds, right? We can think of a sigma bond only, and the contribution will be in electronic contribution will be one electron. Like for example, let's say any, like we have previously shown these kind of examples in the previous slides. So if you see, there is MC bond, one bond. So if you cleave, homolytically cleave, this will be here, this will be, because bonds are consist of two electrons. So here it will be one electron and it has another electron. So contribution will be from this ligand will be one electron. Fine. And MCH3 again, M dot CH3 dot, so it will be also contribution will be one electron. Fine. Now sigma bonds. Sigma bonds, two electron I have written. But these are also sigma bonds, right? But here metals are actually attached with ligand through sigma bonds. That is a different thing. That is general thing actually. Here specifically sigma bonds are donating electron, means if we write like this, like this. Okay. Here H sigma bond actually donating. So we know that sigma bonds are consist of two electrons. So it is donating, and it is neutral. In neutral, it is not charged, right? Sigma bonds, no positive negative charge. So it is donating by two electron only. Simple in neutral method. And next, pi bonds. Okay, neutral ligands. Neutral ligands means it can be H2, it can be NH3, it can be PH3. Okay, so any ligand which doesn't have charge, only lone pair is present. So examples, if you remember PH3, actually you will see in more amount and in more more questions, PH3, NH3 and let's say H2O. So they in that case actually you have to consider two electrons. Okay, like this, because they are contributing to through the lone pair. There is no positive negative charge, nothing. So they are contributing to lone pair. Lone pair has two electrons, so two electrons. Fine. Pi bonds. Pi bonds are doesn't have any charge. So again two electron. Okay. Negative charge. Okay. Let's say halogen molecule. Cl minus. F minus. You can be confused with that, because here for the case of lone pair we are taking two electrons, but here we will take 1 electron. Okay, so please remember that for negative charge we will be taking only 1 electron as a count. Fine. If you remember this kind of these examples and how many actually they are contributing, you can solve any question. Okay, MCL -1. So just for recapitulation, so in neutral method, if you see any metal, carbon or any sigma bond between a metal and anything, mainly carbon is there. So that will be homolytically cleaved. Okay, so contribution will be 1 electron. But if there is like HH, sigma bond is donating to metal, that time 2 electron, as sigma bond has 2 electrons. Neutral ligands, it donates through lone pair. Okay, the contribution is 2 electrons. Pi bonds has 2 electrons, so 2 electrons. Negative charge. For the case of negative charge, it is very important because you can be confused here. Okay, so negative charge, you remember one negative charge is there, so 1 electron will be contributed, right? Now coming to some important, okay, some questions. Here again, the hapticity case, we have taken that example. So hapticity was 1 as the donation to 1 carbon. But what will be the electronic contribution here? Is it 1? No, right? 3 bonds are there. So we know we have to homolytically cleave 3 bonds. So metal and C will be 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. So total 1, 2, 3. So -3 and C -3. So total contribution after homolytical cleavage is 3. So 3 electron. Okay. Now here Hapticity was 3 carbon. But what will be the electronic contribution? So see, this is pi bond. 2 we know for pi bond. And here from this carbon to metal it is sigma bond. Metal is attached to sigma bond. So homolytical cleavage will be 1 from this carbon. So 2 plus 1 will be 3. So electronic contribution will be also 3. Here it is, see, from pi bond actually it is not donating electron. Here only sigma bonds present between this metal and carbon. Again homolytical cleavage and it will be 1. This, so here the whole pi bond are actually attached to metal. All are donating towards metal. 4 carbon atoms and 4 carbon atoms, forget about this. So eta 4 will be there here, forget about this. But here 2 pi bonds are present, right? This one is the ligand, actual ligand. Right? So 2 pi bonds means 4. So 4 contribution in electron is 4. Here, if you see, so you know that carbonyl is stable, CO is stabilized in CO plus and minus. Okay, you know it. So you know it, but and you also know that for negatively charged ligands like Cl, if that time we take 1 electronic contribution. But you have to remember that this kind of carbonyl actually very important ligand. So it is actually the uh, sigma donor and pi acceptor kind of ligand. Okay. So for this case, you have to treat it like a neutral ligand. Okay, CO, just CO. You remember CO. So it will donate 2 electrons like neutral ligand. Okay, this you please remember, keep in mind. And for the case of NO plus, you have to remember that one also, NO plus. So NO, for the NO plus, okay, I will talk you in the later slide also. It will be 3 electrons. Okay. Here These examples are there. First, you tell me what will be the hapticity. Through one electron bond is present, eta 1. Through the 5 electron bond is present with metal and ligand, eta 5. So here, no pi bonds are actually donating electron to metal. Only this carbon is attached to metal via sigma bond. So it is one electronic contribution after homolytical figure. And here, 5 carbons are actually donating. Fine. You can write that 5 carbons are donating. So through homolytical cleavage also you can say that 5 electron will be contributed, and also you can think like that way that these 2 pi bonds are actually donating. 2 into 2 will be 4 plus 1 carbon is 2 sigma, it is donating, so it will be 5. You can think about that also. Okay, in any way you can think about, or you can understand this. So 5 carbons are there. If you think about homolytical cleavage, it will be also 5 electron. And if you think about that these 2 pi's are donating, and here let's say through sigma metal is attached to sigma, so you can think about that also. Okay, so in both ways 5 electrons will be there. Now some important points for electron contribution is that Cl versus mu Cl. Mu means bridging. Okay, mu means bridging. So let's say MCl is there, and in another case there is MCl and M. Okay, so what will be the contribution in that case? So we know Cl is a negatively charged ligand. It has negative charge, so contribution will be 1. But in that case, because from one contribution it cannot donate to 2 metals, right? So we have to see that Cl has 7 electrons. Sorry, Cl minus will be 8 electrons. Okay, fine. So let's just think about that only. Because in neutral method you have to consider you have to consider the neutral form. You doesn't have to know about the consider the negative or positive charge. So 1, 2, 3, 4, 5, 6, 7. 7 electrons Cl has. So let's say to one this one electron it make a sigma bond. Okay. So it has octet now fulfilled. But it has another lone pairs in it, like NH3, H2O, this kind of neutral ligand. They have lone pair. So like that, after the contribution, so first contribution will be the sigma donor. Okay, and it has one unpaired electron, so donation will be uh, through that only first. And it has, if you think about negative charge also, so donation will be first through that, and then after that, let's say this is the one electron donation. Okay, it has negative charge, so one electron donation is there. After that, after the formation of this, you know that it has lone pairs. So now it doesn't have any minus charge in it. It will act as neutral ligands like NH3H2. So it will donate via 2 electrons like lone pair and donate to another metal. So total contribution will be 3 electronic contribution. Whenever in any question you see mu Cl compound complex, you have to take 3 electron for the count, 18 electron count. Okay, so in here it is. So first contribution will be to the single electron. If you consider the Cl minus, so to minus, and after that lone pair will be. Okay, so 3 electrons. And now one important thing, PPH3 versus mu PPH2. Okay, so PPH3 we know, PPH3 it is acting like neutral ligand, and it will donate through it is the in the group of nitrogen, right? Nitrogen family, nitrogen phosphorus. So it has one lone pair in it, so it can donate. But for further donation, it doesn't have any lone pair in it, right? Like the case of Cl. And here, if you see, it is PPH3, PPH2, not PPH3. So, how much electron it will have in its outermost cell? So, phosphorus can form bond 3. One bond is not formed. So, one electron will be here and another lone pair will be here. Fine. Because like for PPH3, this one is there, right? Like that. It has actually P3 configuration. So 3 electron, yes, 3 electron will be there, and 2 s electrons are actually here, the lone pair. Okay, sorry, 2 s and 1 p, 2 s electrons are there. Sorry, for nitrogen, 7, right? 1 s2, 2 s2, 2 p, 3. Fine. This is the thing. Okay. So if you think about this, one lone pair will be there. So after one lone pair, the 2 electron and 5 electrons are there. So 3 sigma bond will be. Fine. sp3, sp3, one lone pair and 3 sigma. So sp3. Okay. So sp3 orbitals are involved and one lone pair is present. So in this case, one sigma bond, as it is not formed, one electron will be here on P and another lone pair is there. Okay. So it will first donate this electron to this. So one electron donation is first there, and after that one lone pair present. So it will be donate. It will donate to lone pair now. So total contribution will be again 3. Okay. So for any group, it is given any new kind of ligand they can give in the question, but you have to just see that what atom is present in the donation, and you have to draw its. You have to have the idea about its outermost electron cell. Outermost, you have to have the idea about the outermost electrons, okay, of that atom. So then you can understand that any odd electrons are if present, first donation will be through that, and after that lone pair can be involved if it has. Okay, it has lone pair, so electron total. Fine. Now linear versus bent NO. So NO ligand can be attached through metal via two way. Okay, via NO plus and NO minus. So for the case of NO plus, the bond order is 3 and it is linear. Fine, it is linear. So it is linear NO, and for the case of bent NO, so it will donate via nitrogen and like this way, linear way, and for the bent NO, it will be like this way. So here bond order will be 2. Fine. So now what will happen is that here NO minus, right? So if you draw the, sorry, here you can't see, right? Below I am writing. So if you NO plus, for the case of NO plus, this is plus, okay? Sorry, no, not it. Three electrons are actually bonded, and it can form 3 bonds, right? And here will be the first. Okay, this is the NO plus, and for the NO minus case, this will be minus. Okay, and it can donate 3 electrons. There is lone pair present. Okay, and it has positive charge, so we have to consider here 3 electrons. Just remember that. And for the case of NO minus, this donating it has minus negative charge, so it will first donate through negative charge, right? And for the case of negative charge, we know, like CLF, we know that 1 electron contribution is there, right? So you have to remember that for the case of linear or NO plus where involved, we have to consider the 3 electronic contribution, and for the bent NO case, we have to consider 1 electronic contribution. Okay, it will be very helpful. Please keep that in your mind. Now coming to the 18 electron rule. So it is a chemical rule to predict and rationalize the formulas for stable transition complex. Fine. But why 18? Why we want that the outermost shell of any metal should be 18, so that it will be stabilized? Why 18? Because let's say for any transition metal, we know that it has d electrons in d, let's say, sorry, in minus 1 d. 3d 4 is like that, in minus 1 d electron, d1 to 10, and in is 0 to 1 and NP. Okay, it will be 1 to 6, 0 to 6. No, it will be 6 actually. H to NP 6. It can vary actually. Okay, it can can be write like this way, and NP 6. Okay, so we know in d orbital, there the highest electron can be filled in d orbital is 10 electron, and for the case of the s orbital, the highest electron can be filled is 2 electron, and for the p, it is 6 electrons. So as a total, if you see that 16 plus 2, it will be 18 electrons. So we know that if the orbitals are fully filled or half filled, that will be more stable. The fully filled orbital actually have greater stability than the other. So for the fully filled orbital, we have to have the 18 electron in its outermost orbital. That's why for any complex, we are looking for actually if it is following the 18 electron rule or not. If it is following, it is stable. If it is not, it is less stable. Okay. Now coming to the various transition metals, because for the counting purpose, you have to have the idea of the valence shell electronic configuration of the transition metals. Okay, so this is 3D series transition metal, and you have to also remember some group wise, like first you have to remember the 3D series all metals, the configurations. Okay, this is the list. And also you have to have the idea that in the 4D, 5D series, which metals are there, so that you can have the idea of their electronic configurations also. Like in the case of zinc, cadmium, mercury. You have to remember like this way. Copper, silver, gold. Nickel, palladium, platinum. Cobalt, rhodium and iridium. Fe or iron, ruthenium, osmium. Manganese, technetium and rhenium, chromium, molybdenum, tungsten, vanadium, niobium and tantalum, titanium, zirconium, hafnium, okay, and scandium, ytterbium. So you have to remember the first series electronic configuration and of course the names, and you have to remember that which metals in 4D and 5D I am saying which metals are in which series. So you know the 3D series metals and their electronic configuration is fine. And if you know that in zinc group which metals are present in 4D and 5D, and in copper, in nickel and cobalt. So you have the idea of their electronic configurations also. Why we are needing this? Because in the questions, these metals are also given. So you have to have the idea about their valence shell electrons. How many electrons in their valence shell? Okay. So electron count for organometallic complex. How we can done this? The valence electron of metals plus electron contributions from ligands, which we have read about, plus overall negative charge on complex minus overall positive charge. If the complex has positive charge, it will be minus with the electron count. If it has negative charge in it, we are counting electrons, so we have to plus it, plus sum it, and plus electron contribution from metal-metal bond. If there is any metal-metal bond, we have to consider that electrons also in the count. Fine. Now valence electrons of metal will be the, we don't, for neutral method we don't have to consider their oxidation state and all. If you see the metal, any metal is given, we have to remember the electronic contribution and we have to total the electrons of D and S. Okay. We have to make the total. Fine. So, for let's say, for example, chromium is given in the example. Okay, chromium is given. So, how many electron uh, we should take for valence electron? We should take the 5 plus 1 will be 6 electron. And let's say for manganese, 3d5 4s2, total 7 electrons. For Fe, 3d6 4s2, so 8 electrons. So like that way we have to count the electrons for metal. Now coming to the example, so this is a simple complex, so I have taken not a organometallic compound like metal carbon bond is not present, but for count 18 electron count we can take that example also. So cobalt is in which series? This one, this has cobalt. So after Fe, it has 3d7 4s2 as a total 9 electrons. Okay, so 9 electrons, let's say, plus NH3 is neutral ligand, so 5 into 2, 5, plus Br is negatively charged ligand, so it will be 1, and overall charge we have to consider. So SO4 has minus 2, so it will be plus 2, and plus charge we have to actually we have to subtract, so minus 2 will be there. And if there is negative charge, we have to add it. Okay, so 19 20, so it will be 18. See, so it is stable. Now coming to this, so chromium in here, so before manganese it has 4s1 3d5. Okay, so means 6 electron. So we have to take 6 electron from chromium, and H2 is again neutral ligand, so 6 into 2 electronic contribution, and here Cl3 means minus 3 charge is there, so plus 3 will be in complex, so we have to subtract it. So now 12, 6 plus 12 minus 3, will be 18 minus 3 means 3. It is not stable. Okay, so this is organometallic. So Fe, before cobalt Fe comes, and after manganese. Okay, before cobalt means there are 9 taken, we have taken, so it will be 3d6 4s2, right, for Fe, so we have to consider 8, and this is bonded to 5 carbons. For neutral method we have to take 5, so 5 into 2, it will be 18 electrons. So this is actually ferrocene compound, so it is very stabilized compound. Okay, now one thing, Cp means CP means this one is CP, this one. Okay. So we know that the here contribution is 5, and cobalt we have taken previously, it is 9, right? 9 plus from 1 CP the contribution is 5, so it will be 10, and 1 positive charge is present, so we have to subtract this, it will be 18 electron. Fine. When you solve the questions, you can understand in a better way. Now some other examples is there. So the practice actually here makes you perfect, so you have to practice a lot. So see, new ligand, you can see a new kind of ligand, but we have to see the donor atom. P is the donor atom, it is like PH3, right? So contribution will be obviously 2. Fine. And ruthenium is in which group? See here. Where is ruthenium? Here, right? So in Fe group, we know that for Fe, the electron count is 8. So it will be also 8. Fine. And PCY3, 2 PCY3s are present, so 2 into 2. And Cl, we know the contribution is 1 from 1 Cl, so it will be 2 Cls are present. And here we have to homolytically cleave the bonds. 2 bonds are there. After cleavage, 2 electrons will be there, right? So 4 plus 8 plus 4 will be 12, 14, 16 electrons. Okay. And here CP means the same 5-member ring, it will be 5. Fe, we know 8 electrons. CO, we have to count it, consider it like a neutral ligand, so it will be 2, right? 2. And PPH3 present, it is also 2. And CF2, how can we consider the electrons in CF2? I have previously told you, we have to have the idea that which atom is donating, let's say for any ligand, and we have to have the idea about their valence shell electronic configuration. Okay, and how many bonds are there formed and how many are left, we have to have the idea. So for carbon, we know that 4 bonds it can form, so 2 it has been formed and 2 is there, nothing charge is present, 2 bonds are there, so it will first form 2 bonds with metal, right? Like this, like this. Here structure is given, but if it is not given, it will be right like this way, right? CHPH. So it is like this only, and it is forming bond, double bond. You can think about double bond. It is formed this kind of bond with metal. So contribution will be 2, right? 2 again. So 8 plus 5 will be 13. 15 will be 19. Okay. And there are no charges there, so it will be 19 only. Now next example is this is the Jaser sort. Okay. So PT has how much electron? See, PT is in nickel group, nickel, palladium, platinum, right? So it will be D8 configuration, D8 and 4s2, so it will be 10 electron will be there, because D8 is 4s2, like that. Okay. So 10 plus 3 from each Cl1 will be counted, and C2H4 means this alkene and this, so pi bond actually it is donated. So plus 2 and minus charge is there, we have to consider is we have to add it in electron count. So 13, 15 and 16, it has 16 electrons. Okay. Now coming to the questions, this is asked in CSIR-NET June 2016. So identify the species those obey the 18 electron rule from the following. Okay. See, straightforward questions are actually asked from this topic. Sometimes a little bit they are asking in a different way, but sometimes these straightforward kind of questions are also asking from the case of 18 electron rule in CSIR-NET. Okay. So See, A for A. Copper is in D9 group, right? D9 means, should we have to consider 9 only? No, right? 4 is 2 present. So 11. 11 from copper, and CP ring, it has 5, and CO means 2. So as a total, it will be 16, 18. 18 electron. Fine. So it is obeying. A is correct. B, manganese, it is D5 configuration. D5 4s2 means 7. 2 CO group means 2 into 2 4 plus 1 CP. Well, 16 electrons. So it is not obeying. It is obeying. C, because here multiple option is correct, right? We have to choose between these 4 options. Okay. C is chromium. Chromium is D4. D4. D4 4 is 2 or D5 4 is 1. So in both case, the count will be 6 plus 3 carbonyl groups are present. It will be 6 again and 5. So it will be 12, 17. It is also not correct. So we have to have the idea that A and D will be the correct option, but see the electron count, because you are practicing now. You have to practice a lot. Vanadium, it is D3, so 5, because S electrons we have to also count, and carbonyl is 4, 8, and CP ring is 5, so 18 electrons. So it is correct. So correct option will be 4. Fine. Now see, in CSIR-NET December 2011, the correct combination of metal, number of carbonyl group, carbonyl ligands, and the charge for a metal carbonyl complex is that satisfies the 18 electron rule. If it is not written here, then also you have to consider here the 18 electron rule. Nothing, no other method is there. Okay. So it is actually they are try to set a question in a tricky manner, but it is simple. The combination of metal also you have to understood, or you have to find out. This is the generalized complex, the number of carbonyl ligands, the X and Z. So everything is given here. So for each case, you have to count the 18 electron, the electron. Okay. So first metal is titanium, scandium titanium. Scandium means D1, titanium is D2. So 4 electron. D2 4 is 2. Then X is given 6, means CO is 6. 6 into 2, 12. Z is 1, 1 negative plus 1. Okay. So it is 17 electron. It is not obeying 18 electron rule. It is not correct. The set is not correct. Now B. B, in the case of B, vanadium is given. It is D3. So D3 4 is 2 means 5. Now X is again 6. So 12 from carbonyl, and Z is 1. So we have to add 1. So it is 18 electrons. So correct option will be obviously B. But let's see the C and D options also. Okay. So C has cobalt. Cobalt means D7. So we have to count 9. And X is 4. So 4 into 2 for carbonyl will be 8. And Z is 2. We have to add 2. So 17, 19. So obviously wrong. And for the D case, MO, molybdenum is given. So it is in chromium group. Chromium, molybdenum, tungsten, right? So for molybdenum, we have to consider the chromium, the electron count as chromium. Okay, chromium, molybdenum. So 6 electron and 5x means 10 and 1. So it is 17. So it is also not correct. So correct option is obviously, we have seen in previously also, correct option is. Now the pair of complexes or ions that doesn't obey the 18 electron rule. See, doesn't obey. In the questions, these words actually can be confusing, or uh, you can actually cannot see sometimes this kind of words. Okay, so doesn't obey means we have to count again, and which doesn't obey, that will be the correct option. Okay, first, okay, pair is given. So doesn't obey 8 electron rules mean the pair. Okay, so for both actually we have to count. So vanadium, scandium, titanium, vanadium, B3, so 5, and carbon is 6, so it will be 12, means 70. Okay, one pair doesn't follow 18 electrons, so we have to see other, obviously. Titanium, scandium, titanium, so it is D2. D2 means 4 we have to take, and Cp2 means Cp, if Cp 5 electron, so it will be 10, and 2 chlorine, so 2. Here will be 16 electron. So both the pairs are actually doesn't obey the 18 electron rule. But let's see the other options also in a quick manner. Mn 7 electron plus Br 1 electron plus cobalt 5 cobalt, it will be 10. So it is obeying 18 electron. So we will not see the other pair. Okay, if one is obeying means it will be not the correct option. Cobalt is 9 electron we have take, and 3 carbon is 6, PPHT 2, 1 negative charge 1. So it is also 18 electron. So we should not see the next pair. So Fe is, we have to take 8, and carbon is 10, 5 carbon, so 18 electron. So it is following again. So these are not the correct option. Correct option is 1. So now one important thing is that by using 18 electron rule, we can calculate the number of metal-metal bonds. So this is a application of 18 electron rule, and from this also many questions are actually in the exam. Okay, from these actually this is very important, the counting of metal-metal bond. So yes, we can actually count the metal-metal bond for a organometallic compound by using 18 electron rule. Okay, so I will show you through questions only, the previous year questions. Let's see this CSIR-NET June 2019 question. So in the question it is given, the direct question is that the number of Ni bonds in CpNi mu PPH2 whole 2 means this complex and whole 2 is there. Okay, so we have to consider if there is any metal-metal bond present or not. Okay, how can we consider? Again the 18 electron rule. So for 18 electron rule, we know that we have to consider the metal valence electrons. Okay, and here whole 2 is given, so we have to consider, we have to take actually count the double of the each electron. Okay, NiD8 means 10 electron, and if we double it, it will be 20 plus Cp 5, we have to double it, 10. Another ligand mu PPH2. Okay, see again, I have actually previously told it PPH, PH, and another bond is bonding electron is, it is not bonded actually, this electron, and another lone pair is present. So the contribution will be for mu PPH2, and it is whole 2 means 2 mu PPH2 is there. The contribution will be 3 electron for each, because one non-bonded pair is there and another lone pair is there. 3 electrons, and 3 we have to double it, 6 electron. Okay, now coming to the, when while I was showing you that how to calculate the 18 electron rule, there another added thing was there, that metal-metal bond should be also considered or count in 18 electron count. Okay, if let's say X number of metal-metal bond is present, X is the bond number, Okay. Then for each bond we know 2 electrons are involved. So 2 into X will be there. Equal to, if it is following 18 electron rule, so will it be 18? No. Here whole 2 is given. So for 2 Ni we are considering. So if 2 Ni are following the 18 electron rule, it will be 18 into 2. So we have to solve this equation and calculate the value of X. So like that way we can understand why we have the value of metal. You see how simple is it? So 30 and 36 plus 2x equal to 36. 36. So 36, 36, 2x will be 0 or x will be 0. So in the option it is given one question. So it doesn't have any metal bond. So what can be the structure? So from the metal bond, to have the metal bond idea, and everything is given because here mu pph2 is given. So which is the bridging atom, that is also given. So we have the idea about the structure, right? So Ni Cp, only Cp is there, right? One Cp for one Ni, and mu pph2, two mu pph2 is given. So p pH2 here will be 1 Ni, and 2 mu pph2 means p pH2 is bonded to 2 nickel, and here 1 Cp ring again present. This will be the overall structure. 2 Cp we have, 2 Ni we have, and mu pph2 2. This mu pph2 means bridging. This kind of structure will be there. There will be no this kind of metal bond. Okay, there will be no metal. Clear? Okay. So like that way these questions are also can be asked, like uh, just the structures are given. Okay, so you have to, nothing is given that you have to calculate the inner bonds or metal bonds or like that. Only in the options the structures are given, and you have to pick the correct option. So in that case also metal bond counting will be helpful through the 18 electron count. Okay. Now coming to the next question, the number of bridging ligands and metal bonds present in the complex Ru2, Ru ruthenium 2, eta 5 Cp. If nothing is given, eta 5, eta 1, then also we consider 5. But see here eta 5 is given, that is fine. The 5 Cp2, CO2 and PH2, CH2, PPH. Okay, no charge is there. So we have to count it. So ruthenium we know in Fe group D8. So we have to, sorry, D6. We have to consider 8 electrons. So 8 into 2 plus 5 into 2 plus 2 into 2 for carbonyl. And what will be here? So PPH2 we have previously seen that PPH2 has one odd electron and one lone pair. So total contribution is 3. But here this is different. Here no odd electron is present because here one CH2 is there. CH2, PPH2, right? So here one sigma bond is there. So no odd electron is present here. But here two lone pairs are present. So if you see any different kind of ligands which are not familiar with, you are not familiar with, then you have to try to draw and try to have, you have to have the idea about the valence shell electronic configuration of that atom, donating atom. Okay, so this is the structure of this atom, this ligand, and it will be bidentate ligand because it can donate to through this and this metal. Okay, so 1 2 3 4. So from this ligand only 4 electrons are coming in neutral. So total electron count will be, okay, it obeys 18 electron count, it is written. We have to count what? Metal bonds. So our count is not done here. will be 2 rutheniums are present, right? Okay, yes. So it will be 2x, obviously. If we doesn't take that, it will be a mistake, big mistake. So it will obey now 18 electron rule. So it will be here equal to, for 2 metal, it will be 36. Fine. Now, number of bridging ligands and the metal-metal bonds. Okay. So now we don't know the metal bridging ligands actually. So see now first, only we will calculate here the metal-metal bond. Okay, because we don't have the idea about that right now. So 16 plus 10 plus 4 and plus 2x will be 36. Now 26, 30, 34. So 2x will be 36 minus 34 and it is 2. So x will be equal to 1. So metal-metal bond is here 1. Mm bond 1. 1 mm bond is present between the two RU. Okay. So in the options, if you see, the metal-metal bond is in the second. So it is not correct, but in these three options, actually, one is given as metal-metal bond. So among these three, any one can be the any answer. Okay. So we know now the metal-metal bond. But from 18 electron count, we doesn't have any idea about which ligand are actually in mu, means which electron are in bridging positions. That we can't tell by calculating the 18 electron rule. Please keep that in your mind. So here it will be like Ru, one metal-metal bond is present, and each Ru has one CP ring. Okay, and one bridging ligand is obviously present here. That will be PPH2, PH, and PPH2. As it is bidentate and two metals are present, it will be bridging. And now question is CO will be where? So in some cases, actually, if you see the structure in later way, the carbonyl compounds, the bridging is also a common thing for carbon. Okay, it can be in bridging position. The contribution will be 2. Again, the contribution will be 2, but it can present in bridging position, also in non-bridging positions. Okay, but for here this kind of compound, it can be seen that you have to know this. Okay, if you know this, then you can answer this. Through this only it is stabilized. So bridging number of bridging ligand will be 3 here. Okay, so 3 will be the correct option. 3 and 1. 1 metal bond, 3 bridging ligands. Okay. Now coming to this question, the set of structure showing the correct hapticity of azulene on the basis of 18 electron. Again, see how 18 electron rule is actually, it can be helpful finding the hapticity of the ligand also. Okay, just you have to count the electrons and equalize. If it is following 18 electron rule, equalize with 18, or two metals are present, 18 into 2. Okay. Okay, first see this set of structures showing correct hapticity. Okay, so we have to actually, for each set we have to count the 18 electrons and see if it is following or not. If it is not following, we have to go to the another next option. Okay, so first it is 5, because this circle is to 5 carbons, so all are donating. Okay, for Fe 8 electron and 5. Fine. Carbonyl 2, 4. One metal bond is present. Don't forget this. And again one Fe 8. Carbonyl 3. It will be 6. And here 1, 2, 3. So this circle is to 3 carbons. So 3 actually it is bonded. So it is 3. Is it 36 or not? Let's just see that. Okay. 13, 14, 15, 16, 17, 18, 19. 36. Yes. Okay. So first one is correct, but we have to see this one also. Okay. For one we are calculating. So it will be, okay, it will be first again 5 and MO, molybdenum. Molybdenum is in chromium group, so it will be 6. 3 carbonyl, 6. 1 metal bond, 2. Plus again 1 molybdenum, 6. 3 carbonyl, 6. And 1, 2, 3, 4, 5. See the circle present in 1, 2, 3, 4, 5. So 5. So 5 carbon. So the donation will be 5 only. Okay. So we have to total it. 5 plus 5, 10. 16. Okay, let's just see from here. 11, 17, 19, 25, 31 and 5 plus 5, 36. So it is obviously 36 will be here. So it is obviously following 18 electron rule, and these also following. So first one will be the correct option. But see, okay, one other option we will solve. Rest you solve in your copy. Okay. So in the second case, if you see, because in the first option only you have seen that two structures are actually following the 18 electron rule, but there are others which are not following. So to show this only, I am solving this also. So 5 for Fe8, cobalt 4 plus 2 metal bond plus Fe8 plus 6 for carbonyl and 1, 2, 3. 3. So again the same thing. It will follow 18 electron rule. Okay, we have to see this one. So again 5 molybdenum, it is 6 chromium group, and carbonyl 6, metal bond 2, and it is 3 from the ring, and molybdenum again 6, and carbonyl is 6. So 11, 17, 19, 22, 28, so it will be 34. So it is not obeying. This is not obeying the 18 electron rule, but this is obeying. But we have to consider the set of structures, right? So in this set only you will find I have shown to you this set. So for the other set you can find out that one will be the, maybe one will follow 18 electron rule but other will not follow. Okay, so this is the correct option. This is also one previous year question of CSIR-NET. See how many questions are actually coming from this only, this topic. Again one question. Identify the thermodynamically stable structure of eta 5 C5H5 Fe mu2 CO and NO whole 2. Okay, this is also came in CSIR-NET February 2022. Okay, this kind of weird structure is given, but let's just see how many electrons they are actually given. Okay. So first, Fe, thermodynamically stable structure should have the 18 electron or should follow the 18 electron rule. Okay. So these we know, and Fe 8 electron, Cp ring 5 electron, NO is here linear NO, so it should donate 3 electron, and 1 metal bond 2 electron, and 2 carbonyl. If it is mu CO also, it will donate 2 electrons. Okay, so 2 carbonyl means 4, and again one Fe 8 electron, Cp 5 electron, and one NO 3 electron. Okay, let's just count that. This 38 will not follow the 18 electron. Okay, so just come to the second point. So here all things are same, only metal bond is not present. Okay, everything is same. See, 8 plus 5 plus 3 for carbonene 2, sorry 4, 2 carbonyls are there, and again 8 for Fe, 5 for Cp, and 3 for NO. Okay, let's just count that. So it will be 36. From these also you can tell, like here metal bond is present. So that's why here 2 we have added. But if 2 we have cancelled out from this, it will be 36 obviously. So it will follow the 18 electron rule and it will be stable. So 2 will be the correct option. Let's just see one option, one other option. So 5, and here no linear NO is present. So bent NO means 1 electron. And Fe is 8, 1 metal bond 2, 2 carbonyls 4, and again 8 for Fe, 5 for Cp, and 1 for NO, sorry, bent NO. It will be 10, 18. Okay, 6, 34 will be there. Okay, so it is also not following. See, 2 will be the correct option we got already. Now no more questions are there. So we have solved various kind of questions, like all are different, but it can be solved via 18 electron. Sometimes you need to know the which ligands can be in bridging position, and you have to know the structure of specific carbonyl, actually carbonyl compounds, organometallic compounds. So you have to have that idea, but rest actually we can solve via 18 electron rule. So you have to see the contribution from ligand, that is very important. So practice more, taking various kind of ligands and see which amount of electrons actually they are donating. That will be helpful for this topic. Okay. Okay. Till this, I will actually end this. So thank you for watching and see you in the next class.